Well, thanks for coming. Today we're going to talk about graphs for genealogists. I'm Dave Stumpf, and Wei is right up front here, is going to help me out when I get in trouble with the visualization stuff. So the agenda for today is to really lay out for you the genealogy landscape and the multiple graphs that exist in genealogy. A lot of the work I've done in developing a plugin has been optimizing the schema for genealogy analytics. And the main goal of this is making recommendations for further research in genealogy and visualizations to make this a little bit clearer. One of my main reasons for being here is to seek out some collaborators. There's plenty of opportunities to participate in this. This is an open source project. So there's a web page listed up on the top there, and this takes you to this kind of a page where you can look at the various opportunities to get involved with this. So I would encourage you to think about that as we proceed through this talk. So I wanted to give you a view of the workflow that we're dealing with here. And we really start off with the data, which really consists of family trees, then DNA data, and then genealogists, of course, have their own vocabulary and ontology, which we incorporate. So in ingesting the data, we have this new Graphs for Genealogy plugin, and it performs the ETL. We also are using APOC, and we have some curated files, things that genealogists are familiar with, where we can link the family tree data to the DNA matches. That's a curation process. And then we bring in reference data as well. So in the knowledge graph, the components consist of that data. Using this plugin, we're using GraphXR as one of our major visualization tools. And then we also do use the GDS plugin from Neo4j, which we'll talk about too. So we have a lot of use cases. This is just a partial list, of course, family trees, pedigree analysis, but then we're looking at DNA matches and the communities they form, some supernodes like triangulation groups, fan groups. And really, this is the main thing we're looking at, is these actionable insights that can take a genealogist into their research in an improved way. And then we have a couple visualization tools. One is DNA Painter, and the other is GraphXR, and I'm sure there's other opportunities here as well. So here are the kind of graphs that genealogists deal with today. Typical pedigree charts. We can map migration patterns this way. We can create various hierarchical trees like patrilineal trees. We can do visualizations of several sorts. I want to point out this one I'm going to talk about a little bit later. This is the so-called auto-clustering, and we'll come back to that one because there's some issues with it that we're trying to address. So here's how we create the knowledge graph. The GECOM is a flat file, unfortunately, but that's the current genealogical standard. We also have DNA, and we're bringing ours in primarily from family tree DNA at the present time. And we bring in several files there, which we'll look at a little bit later. More aspirational is historical documents, and I'll show you how we're looking at that. But many of these things get into the GECOM as events and sources. And of course, the really nice thing in genealogy in the last couple of decades has been a tremendous amount of data that's now available online and can be potentially tapped into. I've just set up a relationship with Family Search, so I'm hoping I can, build into the ETL process, pulling in data from them as well. So let me just show you one project. This is a surname project. This happens to be my Stinnett family, and it'll give you an idea about the data itself. So the GECOM file brings in, 34,000, 4,000 of which are Stinnetts. we have 66 people in the Stinnett family line who have done DNA testing. So we brought their kits in, and that creates a lot of data, close to 250,000 DNA matches. We have a lot of segment data, and then we bring in reference data from the haplotrees, which we also use. And then, of course, we establish a whole bunch of relationships here, including these shared matches, which we have two ways of doing that, the match by segment and shared matches. So this is an important number that runs 350,000 or so. All of that results in a database which is 825 megabytes in size, and we'll talk about the schema a little bit later here about how we've put that together. So there's a couple of challenges here, and one of them I wanted to talk about. It gets back to this auto clustering. What that does is it takes a set of matches here and puts them on both axes, so that you have the diagonal here is where they match themselves, so to speak, but these others are matches to other people. Now, this is a very sparse matrix. Because most people don't match. And so if you actually do the math, this happens to be from a Stinnett project, you end up having about 3 million cells to get a very small amount of data. If you look at the data we have now, with 300 or so thousand things that we would have to put on these axes, you're talking about 127 billion cells that you'd have to do if you had a matrix, and of course that's computationally impossible. But we've been able to solve that problem by doing graph traversals, which requires some optimization of the graph schema, but it really begins to put us in this kind of a framework where we can go from the family tree to the DNA matches right down to the segments. And that's really, I think, one of the powers of the analytics using graph methods. So here's what we're doing in terms of the ETL we've talked about. We bring in these basic sets of data. We then do some enhancements to the graph. We're doing the schema optimization. We're creating some redundant properties. We're creating supernodes and new relationships, all of which are designed to increase the traversals. Our strategy really is based on making this easy for genealogists, so they don't have to know how graphs work or even how the graph database necessarily works. We're providing them with analytic functions that address their needs. We've made it very modular, which means it's also scalable. You can plug in a module in various different places in the setup, and of course we include the visualizations as well. So again, one of my purposes of being here is not only to evangelize this, but also to look for recruiting early adopters and people who may be able to collaborate and continue to develop this product. So the motivation here, again, just to review that, is to get to success, with little depth knowledge of graphs, make it easy to load the data, things that are familiar to a genealogist. There's a little software package that's menu-driven as well that makes it another way to approach getting to some answers. And we produce reports. And they not only do they get the data that you're looking for, but we also include the cipher queries in those so that people can see what they're like and can begin to experiment with them. And we also offer some explanations, because I think most of us are familiar with the problem of getting people to think about graphs in terms of graph thinking. So that's one of the challenges, is to try to bring people along to think that way. And all of that, we really, are focusing on helping them discover actionable insights. And I use the word discovery, deliberately, because there's things that pop out that you just don't anticipate seeing. And again, it's modular and scalable, which makes it hopefully something of interest to a crowd like this. So here's an example of what we do. This happens to be a query that is looking at matches by segment. And that's a pretty complicated query. It took a lot of time to optimize it and do that. And that's pretty scary for genealogists who've never seen a graph. But the user-defined function is a simple one-line statement. and that could also be driven by a menu in a program. So this is a good example of how we're trying to really make it simple so that people can get to the answers they want easily. So the plugin, again, make it easy. It's modular. We've really spent a lot of energy optimizing the schema. It's an open source project. The files are up on GitHub. And right now it has 135 functions for the ETL, the enhancements, the analytics, and then some queries that are produced for visualization. It does make use of APOC and GDS. And again, that link I gave you before is the same one here where you can kind of see how that works. And here you can see our plugin, sitting in the plugin file. It does require a little bit of work in the configuration file for the database. So here's the schema. And I wanted to talk a little bit about how this all works. So it basically has these several graphs that exist within the database. So if we have these person nodes here, they come from the GECOM file, and they have relationships that create the family tree with your mother, your father, your spouse. We have the unions or marriages and the places that events occurred. So that's all from the GECOM file. We then have the DNA matches up here, and with them comes the segment data. About half of them have told us a list of their ancestors. And one of the strategies in optimizing thing is the curation file will tell you that this person has done a DNA test. So they will be a match not in their own kit, but in somebody else's kit. And so we can then propagate that record number from the GECOM into the DNA match. And that helps us shorten any traversals that we want to do. We don't have to traverse from here to there. We can start here. We can even go further, because if we have ancestors that we're studying, they have a record number here. And there may be segments up here that are specific for that ancestor, so we can even propagate those record numbers up in that far, and then start some analytics there. We have supernodes, triangulation groups, which we'll review a little bit more, which are a collection of segments. Here, collection of segments, and we also have what we call some monophyletic segments, which are specific for an ancestor. We also have the haplotree up here. We're just showing here the Y haplotree and all of the SNPs that compose a given branch, and then we can link that to people who've done Y DNA testing. So that's a rough, quick overview of the schema itself. So for those of you who are not familiar with the raw data, just wanted to review that briefly. GECOM 5 is the current standard that's in very wide use in genealogy software, and most genealogists can get these kind of files from their previous work. It's a very awkward file. It's a flat file. It has a numerical kind of hierarchy, but it's not an XML. There is an XML standard, but no one uses it. And so what we do is, we ask our users to look at their GECOM file, and it has identifiers in there. So this is an individual identifier. Here's a family identifier. Those are used in the curation process. So you take those numbers and you then use those to map to the people who've done the DNA testing. So here's a simple example, which will be very intuitive to, Neo4j people. This particular query is starting with me, a person, is looking at my father and mother relationships, doing 3 hops, and finding the ancestors. So here's me, my parents, my grandparents, my great-grandparents, with the appropriate relationships in there. So that's a very simple thing, but what really becomes interesting is what you can begin to do with that. So here is an example of using the collect function so that you will get a total path in the path order. But even more interesting is using the reduce function. So in this case, we're doing the path from me to an ancestor and creating a sequence of path reduced string. So this is interesting of itself, but you can now start to collect other things here that are based on other things that are in these relationships. So as an example, we can look at the Ahnentafel number. This is a standard numbering system in genealogy. And what this does is it uses the gender, the sex here, and if it's a male, we give it a value of 1. If it's not, we give it a value of 0. So we're using a case when here. And that creates a concatenated bit string. This happens to be a total patrilineal line, so it's all 1s. And then we have a little function over here that converts that to base 2 into a base 10, which gives you the commonly used Ahnentafel number. So we're really using the reduce function to create a concatenated base 2 number. So another example of that has to do with the inheritance of the X chromosome. So the X chromosome is inherited in every way except father to son, because a father cannot give an X chromosome to his son. So a couple of things in here. First of all, you address our plug-in using the GEN prefix, and then you have the function. And in this case, it has a record number as a parameter. This happens to be my great-great-grandmother. So then when one executes this, it returns a series of 5 worksheets in Excel format. So you get, the people who share, the ancestors who share the X chromosome, the descendants who do, all of the people there, and then a couple of other things that we throw in there as well. So just to illustrate how that works, so here we have my great-great-grandmother up here, and these are her ancestors. And the numbers in the brackets here are the record numbers from the GECOM. So those are accumulated. We can do that, and we can create an Ahnentafel using the gender. But here we can see the path itself. So here we're concatenating the genders as we move through this. And you'll notice here that these paths have been filtered to eliminate any MMs, which would be a father-to-son transmission. So we can filter that way and just get the people who are involved with the X chromosome. Now the other thing that we do here, because if you sort, so here we're collecting the record numbers. So this has been called a Dewey string by the people who developed ORDPATH. If you sort by this, you're not going to get a sort that's in hierarchical order. So ORDPATH is a concatenated bit string. In this case, it's a hexadecimal number. And this number sorts by the hierarchical order. So we have a little function built into the plugin that will sort by ORDPATH. I actually was just talking to the Neo4j people today about they could actually add this to something like APOC, and because it's a very powerful way to sort in hierarchical order, because you don't get that intrinsically just sorting by numbers like this. For those of you who use SQL Server, this is the same as the hierarchy ID that's in SQL Server. It's a very easy function. It's like 20 lines of code, and it runs very fast. So I hope Neo4j might actually incorporate that into their assets. So a very common problem, of course, is finding common ancestors. Again, for Neo4j people, this very familiar thing of pointing to a common ancestor from 2 paths. This one's me. Down here is my second cousin. So we're trying to find a common ancestor. So if we just look at this tree here, we could have, one path this way and one path from one of these people up to these common grandparents. And what we can do here, these 2 paths are converging, obviously, on most common recent ancestor, MRC, I may use that term. But now we have 3 variables. We have a path length 1, 2, and we have the number of common ancestors that have been found. So in this case, we would have a concatenated string, which we use as an index, 2, 2, and 2. 2 hops here, 2 hops here, and 2 ancestors who were found. So we have another set of information. Hang on here, let me hit this key. we have another set of nodes in which we can look up this index and see that that's a first cousin. And likewise, if we have other concatenated ones, if we only had one common ancestor because one of these spouses married twice, that would be a 2-2-1, and we can look that up. And likewise, we can look up other things. In addition, this particular set of nodes also has data from the Shared Centimorgan project. This is empiric data, so that we know on average, or the maximum minimum, that other genealogists have reported as to the number of shared centimorgans that go along with being a first cousin or whatever we're looking up. So here's an example of that, how it can get more complicated. So this happens to be me and a distant cousin I have, and we actually share 3 common ancestors, and so we have 2 different relationships to each other. This is very confusing. There's overlapping graphs here. It's very hard to do these things in a typical pedigree chart when you have that kind of complexity. So you can look at this in a more typical, like Neo4j way, and here we see my distant cousin and me, and the pathways up here to this common ancestor here, and his 2 spouses. Now it so happens, it's quite interesting, this man married sisters. So the first sister had a child and descendants, and then he married the sister and had a line that led down to me. So this is why I have 2 different relationships with this distant cousin. Pardon? Yes.
I've got one where twin brothers married twin sisters.
Yeah. So here we can see how this works, right? So we've got, a path of 4 hops, 5 hops going up to this guy. That's the 5-5-1, because I've only got 1 ancestor there. And the other way, we've got 6 hops back up to 2 common ancestors. So that's why I'm both her half-fourth cousin and 5th cousin. Now, the other interesting thing is, how are these children related? Typically, when a second marriage, they're half siblings, but in this case, they're 3/4 siblings. And that's kind of a unique thing that happens every once in a while. And this all actually just jumps out with the analytics. So it can actually get a whole lot more complicated. This is an example of a distant cousin and me up here. And we share 4 common ancestors, as shown with the red arrows, because we have 5 splits where the trees branch but then reconnect at a different point. So this thing, you can imagine doing this in a relational database. But this just pops right out in a graph environment. It's just, you just see it immediately, and no questions asked, it's just done, it's easy. So another problem that you confront when you're doing DNA research is you have this common ancestor couple up here, and you've got all these descendants who are in red here who are DNA matches to each other. And so when you see this list of people, how do you sort of prove that they have a common ancestor? It's not intuitive when you just look at the raw data. So here's another example of simplification. Here's a cipher query that will do that, but all the user has to do is put that list of record numbers into this function, and these people just pop right out of the query. So common ancestor queries are a very common thing in this plugin. There's also a whole lot of other functions that deal with the pedigree. One of those is a patrilineal tree, where you can see the red asterisks and how one goes up just through the male line. That's very commonly used in Y-DNA research. Another example is the matrilineal tree, where you've got, just going up the matrilineal line, which is something that is used in mitochondrial DNA research, because that's inherited only via the mother. And then we've also talked about the X-linked inheritance, where you can go up, everything but father to son. And then we have other things, finding double cousins, relationships of everybody within the project. We can look at genetic distances. We can look at pedigree completeness and what's called correlation of relatedness, which is actually a better measure than I'm first cousin, second cousin, or whatever, especially when you have these multiple relationships. The correlation of relationship is a way to get around that problem. And that's easy to calculate in a graph database, and there's a particular function that does that. So up until now, we've been talking about, one kit, say, one family tree and one DNA. But what really you can start to do with this is to bring in multiple graphs. And this one project I mentioned, we have 66 kits that are involved with there. So that adds a lot of complexity to the thinking. You really have to pay a lot of attention to optimizing the graph schema, keeping all of the relationships that are existent in the database. You don't want to lose the primary data here. And then you really have to do a lot of optimization to increase performance. But if it's properly done, you really have done meticulous management of the provenance of the data. Where did it come from and how is it derived? You actually, despite the fact you're adding all of this additional data, again, we all know this, the advantage is it really doesn't, the performance doesn't deteriorate. You can still do very rapid queries. And of course, you get dramatically better analytics because you got a lot more data to look at in the graph topology. And again, because we could add other graphs if we want to. And that's where other people may bring their expertise and want to add a new graph, and that would be very easy to do. So this is the graph schema again, just to kind of re-emphasize. Now the point of this is to sort of ask, put on your graph thinking cap and what can we start to do with that data? So this is a little summary of the DNA data. We don't bring in the raw data here, that is the primary SNPs. Each kit in family tree DNA will typically have 600,000 or 700,000 data points, but they break it into the shared matches, they give us the segment data, and they give us some ethnicity data. This could be brought in, but it starts to get into other things like medically relevant SNPs and things like that that have some confidentiality problems, and it's out of scope for this project now. And as I mentioned before, we do bring in the haplotrees here. And basically what we do is transform these files into CSV if they're not in CSV, and then we load them into the database. And so this is just an example of the raw data for me and the kind of files that I have in my testing that I can bring into this. So I wanted to, this is a bit aspirational, but this stuff exists offline in other formats right now. But one of the things that you can do with this is you can start to take, say, a photograph and label the people so you know where they are, in the XY coordinates on an image or on a document, and then link them to the people in your GECOM file. And so that's an easy thing to do with the software, and now you have what we would call fan groups in genealogy, which are friends, associates, and neighbors, who you now have connected these people together in a graph who may not immediately stand out to you as being related that way. So, and we do this with PDF documents, with images, and so on, in offline right now for this project, but that's something that certainly can be brought into this. So again, if we put on our thinking cap, we can start thinking about the kind of traversals that we can do and the kind of analytics that are really very difficult to do otherwise. So one of those are the cluster matches. If we start with the match, we can look at all of the matches that are connected to them. So those are represented by these loops looping back. We can also look at the matching by the segments, people who share segments, and start to get new insights about the data. So we might want to speak a little bit about at this point the kind of things that we can do with this.
Well, that's a lot of knowledge is right there. I have to say learned a lot from Dr. Stumpf about this process. So here is the visualization. Oh, thank you. Yeah, so.
You're connected to me.
I'm connected, so that's the connection. The photo, yes. That's good, yeah. So the visualization challenge, as you can see, is pretty daunting. It's a lot of connections, and the thing is a lot complex. And when you have one set of connections together, that's one thing. But then you have multiple domain things, like we have a family trees, and then you have the DNA matches, and if you have other domain information started putting together, that become very, very complicated. So GraphXR is a tool that we developed. It's a 3D visualization tool we developed in Kineviz, and it's designed to display of complex informations, like especially multiple domain. It's both connected graph and also it's high dimensional graph, and also multiple domain of connection. So how do you visualize that? And the one of the specific thing we do is put in the 3D, because 3D allows you to separate different layers of information, different layers of domains. As you can see here, it's like the number 3, you have 2 rings, like they formulate into different domains separate. So if you guys are interested, we actually on the 5th floor, you can find us there at the Kineviz. So talk more later. Yeah.
Thank you. So so this is actually a cluster diagram. This is shared matches, and we've done Levin algorithm on them. So the color coding is different communities, and it so happens that those communities correspond to specific branches of the family tree. So that's a very powerful thing to jump right out. You can then take some of these communities and look at them other ways. For those of you who've done any work on Ancestry, you might remember their DNA circles. That's easy to do in a graph database. Here we have a bunch of kits here and the connections that are the shared matches between them. You can then, though, add another layer of analytics. So here's that circle here, and here's the segments that those individuals share, so you can see very clearly, how those connections occur. And then this is I think the most elegant thing. This is where you get kind of the monophyletic segments, the segments that are specifically associated with the common ancestor. So here we have a common ancestor and their descendants, who happen to, some of them, test, and here's the DNA test kit here, and then here are the segments that are associated with those kits. So this would be typically called a triangulation group, because these people share a segment of DNA. This is actually a sequence of DNA with overlapping segments. And so this is a pretty clear illustration of how that works. And I think it's a pretty powerful thing that is, just tells the whole story in one graph. And this query runs very fast. You can traverse the family tree to the matches down to the segments, and it runs very, very quickly. So like we can do several of the algorithms we've done, the Levin, the modularity, optimization, page propagation, all of them give you very similar outputs in graphs. And then we can take that data and output it into the GraphXR, either 3D, and I haven't done it yet, but they have the capability to do in virtual reality things too, which would be pretty interesting. And then we also have the capability of throwing that stuff out into the DNA painter. So here's an example of a DNA circle, and I want to point out here that most of these people have a number, which means we know who they are, but here's one who doesn't, and this is where you get to the actionable information. This person's obviously going to be kind of interesting to you because it links up with a whole lot of other people in your analytics. And you can then, take that and put it in other different formats, and this is just another rendering of what you saw before. These are actually quite easy to do, and with GraphXR, they also have built-in algorithms for community detection and things like that. And one of the things that Wei and I are working on right now is this Grove extension that they have. And the nice thing about that is that you can set it up so that you bring the data in directly into GraphXR, because it can query the database directly, and then you can click on a link in the Grove extension and it'll render the format that you want. So we're working on some more of that to really optimize that. So lastly, I want to just talk about, we've done a whole lot of things to optimize the schema. And this is kind of the secret sauce and the magic of this. We use, indexes, obviously. We have the user-defined functions. We create new relationships to facilitate the traversals. We, have ways of limiting the start position of those queries with redundant properties and things like that. So there's a lot of things that we try to do to optimize the schema itself. And finally, what are some of the future opportunities? And a lot of that, I hope, comes from an audience of Neo4j people or other genealogists. So this is an illustrative example. Here we are up here with this DNA plug-in, a genealogy plug-in. And this happens to be a law enforcement kind of an issue. Forensic genealogy is a very hot field right now with Golden State Killers and things like that. So you've got all of these law enforcement graphs over here. Their own network. You got the suspects over here. You've got dead bodies. You got in Chicago we had the old Al Capone Chicago outfit, it was called. So all of these graphs, there are people working on this part of it. And one of the things that could be done very easily is to incorporate a Graphs for Genealogy plugin and begin to connect those things together. And you can imagine whatever you're working on, you may have your own graphs, but if this kind of data is useful to you, then it's be pretty easy to plug that in. So I hope that will inspire some other thoughts like that. So with that, I just remind you that we're looking for those kind of collaborators, and this web page with the links that I gave you before has some of those opportunities available. So with that, I'm done. We'll have any questions.